All right, welcome to this live stream with our back-to-back live streams. We are now going to be looking at spatial statistics for version 13 of Wolfram Language. And we've already looked at a bunch of things here, so remind me where we have to look next. Did we get Roger and so on here?
Not yet.
Well, okay, Gosha, can you remind us where we got to last time?
Well, you can open the guide page called Spatial Prediction. We discussed some changes for the names, which are not reflected in this notebook that you're showing, but I put them in the guide page.
Okay. What is it called? Spatial?
Spatial prediction.
We don't seem to know about it. Oh, spatial prediction there.
No space. No.
Okay.
Hello.
Okay. So spatial. Okay, so this is the obsoleted stuff. This stuff in with.
So the green highlights were the older names, and the ones below it are the new suggestions from last meeting.
Okay. Spatial estimate. Spatial trend model. Okay, so this was, we had not fully gone through that, right?
No.
Right.
Yeah.
Okay, so variogram function.
Variogram function is now an option to spatial estimate.
Okay.
Which tells you which model of this local dependence to choose.
Okay, spatial noise variance. That's another option, correct?
Yes, that's another option.
Is it obvious that that's assumed rather than deduced?
Yes.
No, I mean, it's obvious given that you know how it works, but is it obvious from the name?
Maybe not actually.
Because I would have expected that to compute a spatial noise variance.
I mean, it can estimate it from the data as well.
All the worse, because then there will be a function that you could imagine using that's called spatial noise variance that estimates it from the data.
I mean, I'm not sure it would make a lot of sense to estimate it by itself. Like, it makes sense to estimate it in the
I understand, but
presence
the
of
name is confusing. I mean,
Yeah.
where do we have other names where we are assuming certain kind of, I mean, it's like a precision or something, where we're assuming working precision or something, right? That's a case where we're assuming something. Well, okay, where do we assume something about data? What's an option where we assume something about data?
Option. It should be.
Let's see. So I mean, if we called it like spatial noise level or something, or spatial noise, if you call it spatial noise, nobody thinks that's something you can compute because it's not a definite number.
Yeah, it's okay. It would be okay by me. My level is almost better.
Well, especially as there's the automatic, wait a minute, spatial noise. I agree, spatial noise level seems. Spatial noise level seems fine to me.
Okay, good.
All right, next up, what's next? Spatial estimator function. I think we talked about that last time, right?
Right. So see it changed from predictor function to estimator function.
Fine. Okay, now we didn't talk about this spatial trend model and so on, right?
Right. I mean, we did, but we didn't come up with a different name. So this is, this gives actually we did talk about it. We had various names, sort of, this is a model structure or a model family. Do you know what I'm saying? The thing that you give here is either polynomial degree n, total degree
I remember
n.
this. Yeah, right.
Okay. Or constant or free form, which we agreed would not have the x and y's here. That's in order to have formulas instead of functions. I mean, you have, the thing is that even with functions, you have to have the x and y's, whether you hold them hash signs or x and y's, you know, if it's a pure function.
Well, I mean, if we called it spatial trend model function, we'd be pretty clear what it is.
But can you, yeah, I guess we could. And we could just have then say that you can estimate it. You can either give a function that's your responsibility to do your fitting, you know, take your business elsewhere, basically.
Right.
But this is friendly. This is, you know, this thing of giving a, you know, automatically estimating a total degree polynomial model, because otherwise.
Sure. Well, I mean, the spatial, I mean, we've got plenty of cases where function arrow integer does something automatic.
Right.
Family of global trends to fit to data. Spatial trend function.
Sure.
Why is it called a trend? Basically just the thing you're fitting to the data.
Yeah. Just thinking, I don't know the history of trend, but I can imagine that it came from the univariate case where you'd see a sort of a trend in data.
Okay, but okay, if this was called spatial fitting function or something, spatial fit function, what is the function actually doing? What does the function actually represent?
It wants to get the data to be zero mean. That's the goal for what it should achieve. If it
how does
achieves
that relate to the detrending function?
It is a detrending function. It is a detrending stage. But we not.
What's this?
It's not there. We don't have it.
Because it's.
But also don't. I also don't want to make this function that we have a multi-step function, because now spatial predict can no longer be single step.
No, I understand. But
if you're going to have to
explain what this function does,
Roger. It detrends data.
Okay, so this is the function that you apply. What does it actually do? You've got this random hillside, and it's got all sorts of flapping around, and then you apply this function to it, and what does it do? Okay,
so this function is supposed to model that hillside. When you add them together, you get the data that you came in with. So conversely, you subtract that function, and you get the local variations. Do you know what I'm saying? If you add those two together, you get the actual data.
Wait a minute, add which two together now? The thing you
global trend, the global trend and the local variation and noise.
Where's the local variation?
That's explained elsewhere. You know, is
there an option for that?
This is the option.
That's the variogram model. That's the local variation. That's the variogram model, and then the noise, the spatial noise level that we agreed. So that's the part. The point is that the global trend can overwhelm anything that you compute on the level of local variation. So you want to remove any global trend that you know or you notice. So then you actually, you know, this variogram method.
Okay, tell me what there's something plus something plus something gives you
So you can have just the global trend, which is just kind of a special function, which is the left picture. It's a nice smooth function. Then you add some local variations, and then you have your your surface that you actually want to model in this. So what we're doing, we try to remove the global trend. So this is the detrending that happens with the spatial trend model, and then focus on this local variations and noise to to fit the variogram model into this, so then we can have the spatial estimator function. And then when you look at the spatial estimator function, the output would tell you whether there was a linear trend or a constant and such. So when you then query the values, this global trend will be taken into the consideration to give you the appropriate estimate for the space, for this
Okay,
surface.
so let me see if I understand. So then what we've got is we've got spatial noise level, which is what we're assuming about how much wiggling around there is. Is that correct?
Not
No.
necessarily, no.
The two wiggling comes from two things.
Yes.
One is, kind of inherent that actually look at that the last 3 point plots there, those three. If you assume that your data, the value at each point is measured absolutely exactly with no error in it whatsoever,
Yes.
then you would want your surface to go through the points to interpolate. If you don't think that you've measured your values 100% correctly, that means you can't trust the values 100%. Then you want to sort of weigh the uncertainty in those values with how much things are varying in the local dependence model. So the more noise you think that are in the values, the less you should trust the individual values and trust more the values around you, basically. And that's
Yes,
in
I
that
understand.
that's in that dependence model.
Okay, so let's just understand what are the different pieces here. So, okay, what is binned variogram? Is that something completely different?
Yes, it's still a variogram, but it's basically it's also called empirical or a sample variogram, and it's unfortunately not a valid variogram, but it can tell you something about data.
So wait a minute, is it like variogram function, which is it going in or is it coming out?
No,
neither. It's a kind of a data estimation of the model. So this is your this gives you the idea what your model possibly can be, and that's what we then fit to the certain family of models. So
this
it's
is,
like,
is binned variogram an option? No, it's not.
no, it's a function.
No.
It's a little bit like histogram list, in what it spits out.
Well, how like it is it?
Pretty much the same thing, in the sense that not how it computes things, but how it reports things.
So why isn't this called variogram list or something?
Wait a minute. Why do we return weighted data?
Because each pair, so each pair, which is the distance and the mean the mean of the variances for this distance, is also weighted by the number of pairs that you have in each bin. So that also gives you the information on the amount of like reliability, how many pairs you had to obtain this value. And so if you look at this point value plot that we see here, it shows you that the most pairs you have in the middle section of this bin variogram. And then at the end, so for the very large distances and for the small distances, you have fewer pairs. So your whatever you estimate there, it's not so solid as what you get in the middle.
Okay. But here's what you can read off in that diagram, Stephen. If this thing goes to infinity, like this last plot does, then there's a good chance that basically you have a trend that you haven't taken care of.
Okay.
Okay. So then you didn't correctly detrend the data, if you like, or there is a trend that needs to be taken care of.
Okay. We have a suggestion here about looking at this is an explorer that is you zoom. Yeah, I have one of these things. It's the blockchain Wi-Fi thingy. What does it do? As you zoom in, well, that's kind of interesting. Goes to a geohistogram type thing.
Mhm.
Although here it's just showing that the thing is present, right?
What is this for?
This is a blockchain connected. This is tokenizing Wi-Fi access, basically.
Oh, so it has nothing to do with helium at all.
Well, I don't think so. Who
Okay.
knows?
Wi-Fi. Okay. Wi-Fi. Okay.
But anyway, so I mean, I don't know what this is. That's interesting that when you zoom in to the points, I mean, that's a geohistogram basically, except it's a geohistogram which doesn't show how many things there are in a given area. It's just going to a particular scale.
Right.
Mildly interesting. Okay. Anyway,
Might also be the privacy issues that they will not give exactly a Wi-Fi position.
well, yes.
So
Right.
Right.
The okay. So I'm sorry. This is too complicated for me. Go through this again. So hold on. So variogram model. What the heck is this? This is a setting? What is this for?
so
How is variogram model
okay,
used?
so last time we talked about it a bit, and so variogram model, as we decided, it's going to be an output to the estimated variogram model, but on itself, it's also a container of a model. So what you get out of it is the variogram model, and you can see the elided form, and it gives you the type of the variogram and a little illustration plot.
Okay, so estimated variogram model returns a variogram model.
Correct. So that's kind of our
Okay,
the
and then
main
that was your idea from last time.
right.
Okay, and so then what is the thing whose value is set to be variogram model?
That's variogram function in the spatial estimate.
Okay, fine. Okay, variogram model. Well, I would not say a function representing a variogram. I would say a symbolic representation of a variogram model.
Yes, that's a better name.
Yeah.
Yes, but it behaves like a function.
I don't care.
That's
You
fine.
mean that you can apply it to things?
Yes.
Right.
If you have, yeah.
I think we should say a symbolic representation of a variogram model. What happens when you apply it? If you apply it to 3, what does it do?
Should give you the value at 3.
Does it apply to points or R values?
No, it should only kind of give you something reasonable for positive reals.
So scalars, positive scalars, as opposed to
yes.
points in Rn.
Okay,
Yes.
so is variogram function, is the setting for variogram function a variogram model or something different?
So for variogram function, you can input the variogram model. So variogram model can be given to variogram function. I mean, to spatial
As the
estimate via
setting.
variogram function
As
as
a
a
setting.
setting. Yes.
Okay, so
But
variogram
can
function
also-
arrow variogram model of blah.
Yes.
Okay.
Yes.
But you don't, I mean, normally you want the automation to kick in to find it for you. You don't
Sure.
want to.
Which is
but-
then going to basically call estimated variogram model and just
Yes.
figure out.
Yes.
Yes.
So you
Okay.
can give a string and it's gonna estimate the parameters, for example, for the given type.
Okay. And an estimated variogram model returns a variogram model, but a binned variogram
Does not.
returns just the data.
Yes.
Correct.
It's not intended. It cannot be. Actually, here's the thing, Gosha, that should be possible input to estimated variogram model.
Yes, it is.
Okay, great.
Yes.
Fine. Good. So on its own, it can be used as input to estimate a proper variogram model. that can be used for spatial prediction, but can also be looked at and understand something about your data. As I said, when that goes to infinity, when that looks like it's not saturating at that highest level that it saturates at is called the sill. It tells you how much variation.
Right, that's fine, but the result from build vari, I mean, the thing that's really bothersome to me is that the name variogram is like a histogram and it suggests an image, which these are not. None of these are. So the analog of histogram is bin lists, right?
Yeah. No.
Wait, isn't there histogram list?
It's histogram list.
Bin list is slightly different.
Yeah, okay. But so could we add lists to the end of this?
Yeah.
Mm-hmm.
Could you explain? Is it, if we just said variogram list, that would be wrong?
That would not be necessarily wrong, but that would not be precise enough if we want to have different methods to compute sample variogram, possibly in the future.
So bin variogram list is what you are proposing.
I would think that would explain what's happening, that we are doing binning, and that's the method that we're computing the variogram from the data.
So bin variogram list. Okay, we got one more to go.
The trender,
the detrender.
Right.
Okay, so spatial noise level, and then this detrending is, again, I have to remind myself. Where is it? Spatial trend. Okay. Okay, we've got spatial noise level. Spatial trend. Why isn't it just spatial trend function?
It can be. That's a perfectly fine thing.
Okay, that seems like what it should be.
Okay.
All right. What else do we have to figure out here?
I think that concludes it.
Okay.
I have just one question if we are at this, because looking back as the estimated variogram model versus variogram model fit.
You have a suggested alternate name, you mean?
Yeah, I mean, I don't know if we discussed that, but in the way I thought about it after our last meeting, and we have like time series model fit that returns time series model. And so, like maybe this is also more into the fitting than necessarily the estimation methods, which would, maybe connotate with maximum likelihood method of moments, what the fitting with the distributions is,
What I would expect if you do fit is to supply a bunch of properties that give you quality of fits and other data as well.
Don't we have a whole estimated, we have a whole estimated family, so to speak.
We do, yes.
We do.
And isn't this doing something like that? Isn't this basically returning the best guess of a variogram model?
It does.
It does. It gives you the best parameters, the parameter values for a given.
Yeah. Well, but it actually returns the variogram model.
Yes.
Yes.
I think the right name is because our fit functions, somewhat annoyingly in some cases, don't actually return the fitted function. They return a bunch of other cruft as well.
Right. I mean, that was in version 7 was the first time we'd introduced, composite data structures like that. But they do behave, what gets returned actually do behave like a function, even if you don't see the formula.
Right. Okay. Let's see. Any further questions on this? So I think we understand how this is working. I mean, if I wanted to get just naive question, okay? So let's say I've got satellite imagery. And I want to, how do I feed that into, let's say I want to find out the density of lakes in a given area. What would I do? Just for fun.
Yeah, so I think if you want a density estimate, that's what we shipped in 12.2. That's like, you basically kind of have point data, if you like. I mean, it's a crude way, okay, but it is you have to see a lake as a point, but that will take points to densities, and we have a whole family of such density estimators there.
Okay.
That we provided.
Okay. What? Okay. So what does this do?
So image processing, you need something that sort of gives you the points, the locations of where they are, the things that you
Okay,
want.
so pitch what you've got here. Spatial
This one,
estimate.
yeah, this is like you have a bunch of values, kind of like list plot 3D gets a bunch of values, at 2D locations, and the question is, what is the surface that drapes over it?
Okay.
Okay. Because you
so for example, in the lakes example, if I wanted to plot the lake density as a function of position in Minnesota or something, what would I?
Yeah, the density. So here's what's slightly confusing. If you have a bunch of discrete data, you can talk about densities of them, right?
Mm-hmm.
If you have, but the density is itself, in fact, a continuous surface over the space.
Yes.
So that density is, in fact, a field.
Yes.
Okay. So if you had values that said what the density is at the different things, this one can fill in the missing data, if you like.
Okay, so one of them is the spatial point process, where it's just saying there is a lake here. So let's say that I also knew the size of the lake, or let's say I knew the average number of some kind of fish in each lake.
Yeah.
So I've got lakes, and they've got goldfish, whatever, carp, whatever it is in them.
Right.
And so then what I'm trying to do, what you're saying is that spatial estimate would give me the carp as a function of position throughout Minnesota.
Yes. And that's kind of how it started, like this Mr. Krieger was looking for gold deposits. And so what happened is that you would drill a hole and establish what the level of deposits was at that hole.
Right.
Right. Then you would drill another hole. And then you want to interpolate the values in between.
Right, because you have an assumption that there is a process that spewed gold out in the early history of the planet.
Yeah.
And that you are basically sampling that scalar field of gold density.
Exactly.
And you're sampling it at points.
Yes. Yes.
The only pity of all of this is that story of estimating a scalar field, for example, is a more general story than the geo story. I mean, these things that we're building here are very geo-oriented.
No, it works. It doesn't have to be geo.
I mean, they're spatial oriented.
The spatial oriented, but they're
and
not.
Also going back.
I mean, it's taken us a lot of effort to make it work for geo. I mean,
Right.
Seriously, we
yes.
have to
Okay,
fair
geo. Enough.
Yeah.
But I mean, but so what does it mean? Why is it called spatial?
Because
yeah.
Well, because it is
looking at the spatial distances between the data points. So we look at the space distance.
I see. So that the argument is it's living Euclidean space, but I mean everything is.
Right.
But I mean all of our things. List density plot assumes you're living in Euclidean space.
You're right.
Yes, but it's also assuming that you have connections. And so the underlying model for this is that the things that are closer are correlated. So the values will be similar.
Same
and for the things
density.
farther, they're going to be.
Yeah, so list contour plot assumes the same thing.
Right, but the way that you do your interpolation, it's not necessarily linear. You don't go with the line, but you have these different models that come from the variogram computations.
But so why is it the case? Let's imagine that we do list density plot. Okay, why are we not using all this technology to make better list density plots?
We will. It's coming, Stephen, and that's a discussion we're going to have probably for 13.1.
Yes.
But
And
okay,
Thank you, Stephen. Good tee up.
What?
Well, you just said what I tried to say before earlier.
Okay, but hold on a second. What I'm concerned about is when we say spatial statistics, what is it that you wouldn't think of doing? I mean, so
and a lot of people have actually asked for this because the quality of sort of list density plot when you don't have dense data is not so great.
Right. I mean, but this is the same story as the story forever of should you spline your curves when you don't have adequate data.
Yeah, it is. But this one gives you, so this one gives you. We talked about these two knobs, right? The local variation and noise. This gives you a way to trade them off. It gives you sort of the right knobs basically to trade
I understand,
them off.
but if we're doing all of this and we're going to make list density plot be able to essentially spline its data, I mean, not in actuality, but something like that, right? The generalization of splining its data. I guess we have interpolation order for list plot, which does the same kind of thing.
Yeah. So we're going to have to probably come up with a new, if you have a brilliant idea there, I would be.
Well, okay. So does list density plot have an interpolation order right now?
Yes.
Which means what?
Which means it actually is using splines, interpolating splines. Okay.
But then this is a whole different way.
But I think that there's some technical limitation. I can't remember now exactly. I think it doesn't work for irregular data or some such, if I recall. It works only for regular data, I think.
Well, but okay, but so fine. I would not totally surprised. But basically, what this is doing is it is providing. Okay.
There's a good example.
So similar to interpolation. Go ahead. What are you going to say?
There's a good example, the ozone example, right? Like with the big gaps that maybe can help you see how it kind of works.
Where do you have that example?
In the spatial estimate.
And also, Stephen, going back to your lake example, you can imagine that you want to map the bottom of the lake and you sample the depth, at some points of the lake. And so that could serve you to create a surface, the bottom surface for the lake.
Yeah, this is such a weird business. I mean, this is such a frigging weird business. Because this is just like splines and curves. It might be right or it might be nonsense. And the question of what's true depends on the underlying thing that is generating this. I mean, ozone may be such that it obeys the fluid equations or something, or maybe, I don't know, maybe it's magnetohydrodynamics more or something, but
But you're right, Stephen. So that's a question of models. When you use models to fill in.
Yeah, because you're just garbage. I mean,
it can be, yes.
Right.
So, but even interpolation itself is
a model.
Yeah,
it's a model.
Yeah.
I mean, the only question is how insidious the model filling in the missing data imputation ends up being.
Yes, exactly.
Right. I mean, of course, we humans do it. The standard optical illusion where you put you look at something with one eye and you have a big blot in the place where your optic nerve comes out of your retina, and you just see the graph paper continue. That's us doing interpolation.
Right.
Which we do all the time. And where the fact is, in that particular case, you got it totally wrong because there was actually a big blob there. Right. Okay, well, interesting stuff. I think what you're saying here, I'm just trying to understand. Here's the thing that I'm trying to understand. This is a general way of interpolating scalar fields given point data, right?
Yeah.
And my question is, there's nothing spatial about a scalar field. It's just values. It's no more spatial than list density plot is spatial. Am I making sense?
Are you going metaphysical on me now?
Well, not terribly.
Okay. Well, the spatial may be in the sense that you have to find metric, you have a distance way of measuring distances between your data.
I see. As opposed to list density, I see. But list density plot doesn't really care. Fair enough. Okay. Spatial. Okay. Okay. I get it. It's nice. There's a comment here. Yeah, there's a comment about auto completions. Yeah, we're working on fancier, bigger, stronger auto completion. Not for this meeting. And there was
Auto completions are great, everybody, isn't it? I think that's one of the automation things that we built that's just great. And
Yes.
we want more of it.
We want more code assistance.
Yeah, we want more of
code
it.
assistance.
More of it everywhere.
Right, but
we'll get into the situations like when you type in Messenger or something like that on your phone, where it auto-completes slightly wrong, and it's sometimes embarrassing. It's like, oh no, didn't mean that.
Yeah, right. Well, but the thing that we're really going to is code assistance, where you have kind of spell checking squiggly lines under code that we think is sort of heuristically likely to be wrong, and so on. And that's what we're working towards.
That will be great.
I know that's what the whole big effort, Roger.
I know. I see it from a distance. I'm just not in the trenches with it. So
yes, well, it's got a ways to go, but it's getting there. And I mean, hopefully, eventually, the type analyzer will be able to be hooked into that as well, which will give us a bunch of other information. All right, we should wrap up here.
Okay.
Thanks, guys. Good stuff. And thanks to folks on the live stream. And see you another time.
Okay.
Bye for now.